So now we have looked at all the different ways of finding a derivative function. We have the product rule, we have the quotient rule, and then we've got the chain rule. We know how to take the derivative of functions that's power functions that have exponents, either integer value or decimal value, radicals. We know how to do those, subtract 1 from the exponent. We know how to take the derivative of an exponential function, e to the x, 2 to the x, all those kind of functions. Again, e to the x is its own derivative, and then we use the chain rule to take the derivative of that exponent. And then we also know how to take the derivative of a logarithm. The natural log is 1 over x. So we've got all these tools that we have for taking derivatives. In chapter 12, we are going to apply those tools to solving, I guess we call them real world problems. They're just problems, specifically dealing with business. And in this first section of 12.1, we are going to take a look at finding maximums, highest value, and when we're looking for a maxima, which is, I guess, the Latin version of maximum, we're looking for the highest y value, but we identify it by its x value. Okay, so that's one of the confusions we'll work through. The x value gives us the location. The y value tells us that it's a maximum because it's the highest of anything around it. It's like at the top of the mountain. Or it's a minimum, which means it's a y value that occurs, the lowest y value at a given x value. So x value is the location. The y value actually tells us whether it's a minimum or maximum. And a minimum is like, think of it as being at the bottom of the valley. You're at the bottom, everything around it goes up. So that's the concept we're going to focus on today. We'll call first relative extrema, which is the extreme values, either high or low, in a given area. And then we'll look at absolute extrema, the extreme values that for the whole function, what's the biggest, what's the smallest. So what I want to start off with is, this is similar to what you'll see in your first homework assignment. It's a very visual thing. You can look at the graph and you know it's a maximum because it's the highest point. So we can identify right here, that's what we would call a maximum. Now, if we don't know what else is happening, we know this is a relative maximum because it's in this area, it's the highest. Now, since it's stopping here, we're also going to see that this is also an absolute maximum. It's the highest of the highs. Okay, and we identify it that at its x value, we've got a maximum of 8. So notice every maximum or minimum point has both an x value and a y value. So we say the maximum is 8 at x equals -4. So the -4 locates it. The value of the maximum, though, is actually the y value. And then you'll see a minimum over here at +4. So we've got the point 4 comma -4 gives us a minimum value. So we have a minimum. The minimum is -4 at x equals 4. So that's kind of what we're going to be working with today. Now, we don't want to forget about these endpoints, because notice this right endpoint is a maximum for its area. It's the highest point over in this general area, in this neighborhood. So we call this also, this is what we definitely call a relative max. Okay, and the relative max of 4 at x equals 12. Okay, over here we've got a relative minimum. It's not the lowest of the lows, but for its area, for its neighborhood, it is the smallest y value. And so we would say that we have a relative minimum of 0, notice that's a y value of 0, at x equals negative 12. So we'll find ways of listing it and such, but you've just got to remember that every time we've got either a minimum or a maximum, whether it's relative or absolute, we are going to identify it. The location gets identified by the x value. The actual value is identified by the y value. Did I say that right? I hope so. Anyway, let's move forward. So this is a PowerPoint provided by the textbook company. So I'm going to go back to use this and see how it works. Give me your feedback. I want you to also see the language that's getting used mathematically as we apply things. So again, we're looking at graphs as one of the easiest way to see minimums and maximums, and you can just kind of see it. Well, here that looks like, for that area, that's a minimum. Maximum. There's another maximum. Here's a maximum, and then we could start looking for minimums. There's actually one here. We're going to see that's kind of going to give us a special value. It's going to have a special name because you actually cannot take the derivative here because we got this sharp point. We talked a little bit about that, I think, hopefully. So the derivative does not exist there. Here we also get a minimum and a minimum here. Okay, and the slideshow will identify relatives and minimums and absolutes and all that kind of stuff. One of the things you might notice, if you were to draw tangent lines at this particular one, the tangent line would have a value of 0. It would be a horizontal line. Same thing down here. So early on we'll see with minimums and maximums, if we can take the derivative is going to be equal to 0. So that's one way. One tool we're going to use is take the derivative, set it equal to 0. That will give you either a minimum or a maximum. It doesn't find all of them because there's like I said, there's a place here you can't take the derivative, but we can still use the derivative to test what's happening on either side to know whether it's a minimum or maximum. Okay, and again, also here you'll see that. Now we can't take derivatives at the endpoints, so those we're just going to have to either look at the graph or get function values near there. Okay, so I won't read through the PowerPoints, but I put them here so that you can take a look if you see anything of value to read through. I will highlight a few of these, and again, you can always pause the video if you need more time to read, or you could fast forward if you're getting bored. Okay. So we've got the highs and lows, and again, they're identifying the x values are where the things occur. So we identify them, the maximums, by the x values. So there's a maximum, there's a maximum, and there's a maximum. So that's what identifies them. What makes the x value of p be a maximum, though, is its corresponding y value, obviously. So it's the y values that give us the ability to see which one, in comparison. We can see over here to the b is going to be our absolute maximum because it's got the highest y. These other are relative maximums for their area, but they've got various different ones. And then we do the same thing with the minimum. Again, the x values locate those values. So we use those x values to refer to them because it tells us the location, but it's their y values again in relation to the points that are around them that make these either relative or absolute minimums. Okay, that's the concepts. We can do most of this graphically, graph it, and that's what I'm going to request you to do. If they don't show you the graph, if they give you a function, graph it first. Take a look, visually look at it. You'll be able to identify, for the most part, minimums and maximums. Then use the calculus to verify it. That's kind of the approach we'll take. So, this one's very wordy, but we'll define it. Relative extrema is just a word for relative extremes. So, you know, they're using these Latin endings: maximum, minima, extrema, maximum, and extremum, singular forms and plural forms. But I think the English I use, the high points and the low points, a lot clearer for me. And again, what we do is all this is saying is we identify their location by their x value. The x value gives us the location. The y value gives us whether it's a maximum or a minimum, and so forth. So, yeah. So again, x values give us location. The y value tells us whether we have a minimum or a maximum. Okay, and again, like, you know, maximum, think you made it to the summit. You're at the top of a mountain. Minimum, you're at the bottom of a valley. Everything's going up from there. So that's the way I would look at it. Okay, so now we're going to get more detailed mathematically. This might remind you of the approach we were taking with limits, although we don't have, fortunately maybe, we don't have to go too far into this. So we take an x value, r, and again they substitute all, but there's some value here, some number here, and if we go a little bit to the left, that's this one, right? A little bit to the left, a little bit to the right, and that h could be anything. It could be a very small value, it could be a little bit larger, but we're just saying if it's, you know, small enough. You're too large, you're out of the neighborhood, right? So it's thinking, we're thinking, let's just see the neighborhood area. A little bit to the left, a little bit to the right. This r value is a maximum if its y value is bigger than all the other guys. And mathematically, what does that look like? Well, it's saying that a little bit to the left, a little bit to the right. If you do that, the biggest y value, that's what this is, right? This is the y value at r, is larger than all the other y values in that interval, in that neighborhood. Okay, and you can make h smaller and smaller, and then as far as you need to. You make it a little bit larger, just depends. Some maximums are a maximum for a very large neighborhood. Some are only a maximum for a small neighborhood. It's a little speed bump. Some are mountains, some are speed bumps. Okay. Same thing happens with the minimums. We can go a little bit to the left, a little bit to the right. The difference is that the y value is the smallest of all the other folks in the neighborhood. Okay, this is the y value of everything else is larger than that last little valley, the bottom of the valley. Okay, and again, just some mathematical notation. Here's our interval. We're at r. We go a little bit to the left, a little bit to the right. This is what we did with when we were talking about limits and trying to get that slope to one point. So that ties back to that. Fortunately, we're not going to do a real formalized definition with limits and all that kind of stuff, but because we can also see it graphically. Okay, so then we come back to our example, and looking at relative extrema, we see that P and R we would identify as relative maximums. We could also call B a relative maximum, but we're also going to see that it's got a special name because it is the largest. It is going to be our absolute maximum. But again, sometimes you don't know if you don't see the whole picture. You can call it a relative until later and just say, oh wait, but this one, yes, it's relative because it's in its neighborhood, but it's also bigger than everything else, so this is an absolute, and these are relatives, relative axes. Okay. So let's talk about absolute, right? What does that mean? Well, then that's when they talk about B. Okay, because at x equals b, there's our absolute. It is the greatest value of all times. I am the greatest. It's the Muhammad Ali of points. I think Ali was, at least he was the greatest orator. I liked all that. He was fun. He seemed to be full of himself, but you know, he had a humor about himself. And it was kind of cool. He lived here in Arizona, didn't he? Phoenix, I think. So, absolute value, the greatest value of the whole graph. Okay, and that's really all we got to say, is that it's bigger than everything else. So the y value, again, we locate it at an x value, but its y value is what is bigger than everything else. So this is, sometimes when we start doing this analytically and we get all this stuff, we get confused. We're trying to compare x values when deciding on a maximum or a minimum. We're really comparing the y values, but we report it by telling the x value that it's at. Okay, because that gives us, the x value gives us location. The y value gives us elevation. So that's how kind of we want to think of that. And again, minimums are just the reverse. The absolute minimum is going to occur at a place where the y value is lower than everywhere else. And you're looking for gas, you want to maybe go to the place that's charging the least amount, right? You want that minimum. You want minimum costs. You want maximum profits. So these are the two types of things we look for. And again, it does give us a point coordinates, you know, x comma y. So again, x determines the location. The y value determines the elevation. You know, so it's pretty straightforward once you get going on it. When I was learning all these things, too many years ago, actually, geez, that was 40 years ago, back in the 1980, I graduated from high school. Wow, that just scared me a little bit there. But we didn't have graphing calculators. So we couldn't always see what we were doing. We had to use these techniques. What you get to do with the graphing calculator is you can see it first, locate them, and then use the calculus to verify. So that's why we get to start with a graph. And so if we do that, we see that an interior point S actually ends up being the lowest y value of the whole thing. So we get a minimum at S, and if we label this point over here, we'd have its y value. Okay? We just kind of keep going through this. So now we're going to start making the tie between actually having a function and its graph. So if we were to graph the function f of x equals x squared plus 1, it's a parabola opening upward. So we've been doing this. It's also the vertex. So we've been finding points like this for a long time. Parabola and x squared function is going to have a minimum, or again, its maximum, depending upon whether it opens up or down. And what we see is that everywhere else, right, when x is 0, everywhere else is bigger. All the y values are bigger if you go to the left or the right. So that makes this point here, 0, 1, an absolute minimum. Again, the x value is the location. The y value would give us the elevation or the minimum value. Minimum value. And this is always location. It's the x value. And so the point itself we can label as an absolute minimum. Okay, and you see it. And what we're going to do is we're going to also now use this or a similar one to show how we can do this with calculus as well. One of the things you'll see is that if we have an absolute maximum, say in this case, if it has an absolute maximum, there's actually only one maximum value, because if there was something a little bit bigger, that would be the maximum. You can't have two different maximum values. However, you can have that same maximum value, right, occurring at two different locations, such as this. This would be probably an x to the 4th type function, and it actually has two places where it has a maximum value. The value of the maximum, though, the y value, is the same there. So we define that as there's one value of a maximum. It just occurs in two places. You think of the sine curves. Again, if you've done trigonometry, you could have multiple places where you get a maximum, but the maximum is only one number. Okay, there's only one, because if something else was bigger, then that would become the maximum. You can't have two biggests. Okay, let's keep moving. So now let's get into some techniques for locating extrema. Okay, and some definitions. Now, occasionally, in the homework, there's a couple of these, and these what we're going to refer to here as singular points. We can't take a derivative here, and you're going to see that occurs with rational functions. So if we've got like a x to the 1/3 power, any exponent less than 1 is going to, because when you take its derivative, it gives us a denominator. Where a denominator is equal to 0, you can't take the derivative there, but there is a function value here. So we'll see a few of these examples, but in reality they're fairly rare unless we're dealing with radicals. I guess radicals do have them, but and it would be only odd radicals, a 1/3 power, because a square root starts at a point and goes off, so it's got this point. It doesn't have a singular point, it has an endpoint. But when we're doing this, what we do is we find what we call critical points. We're going to define those. That's any of these points in the middle, and a singular point is a critical point. So these are all critical points. You'll notice that they've got the tangent lines are horizontal. So primarily critical points are interior points where the derivative is equal to 0, or where the derivative doesn't exist. So we'll look for these singular points, but on the graph they're very noticeable because they're a point. They're not a smooth curve like this. Okay, but then we always need to remember we can't use calculus for this, but we have to come back to the endpoints are also places where often we get they're often a relative minimum or maximum generally, because if it's going down or up, unless it's constant. However, and they could also be the absolute max or min, as in this case, the right endpoint is the absolute maximum, but the left endpoint here is not the absolute minimum. There's something actually smaller. But those are the things we look at. We look at critical points, which are interior points, and we look at the two endpoints. That's what we have to remember to do. So what they call stationary points are where the derivative equals 0, because you'll have a horizontal tangent line there, and then they're going to define here for us what a singular point is. Okay, so we've got stationary points. The rate of change of f is 0, so that's, the derivatives equal to 0. So wherever the derivative is equal to 0, we get a stationary extremum, a minimum or maximum. And we'll look at some ways. Best way, look at the graph. Is it up or is it down? If we can't see the graph, we'll look at ways we can deal with that. Okay, and again, the x value gives us the location, and the y value gives us the value. And now there could be not a horizontal tangent line. There could be a place where the derivative is not defined. Okay, so like the absolute value of x, they're giving us this example. That's what we're going to call the singular point. Okay. So, and again, I looked through the homework. We do have 2 examples of this in our homework. So there will be a singular point. You won't be able to get the derivative because the derivative doesn't exist at that singular point. But from the graph, you'll have to look at the graph and you'll be able to get both the x and y values. Okay. So again, here's a more formalized. Critical points are what we're looking at. Those are the interior points, so not the endpoints, but the interior points. And there are places where either the derivative equals 0, horizontal tangent line, or it's not defined. Okay, and if it's not defined, that's a singular point. If it is defined and equal to 0, that's what we'll call a, what do they call it, stationary, right? And again, we don't have to remember these words as much except for when they're asking for them, I guess. So singular point is where it's not, the derivative's not defined. Stationary points are where the derivative is equal to 0. And then don't forget about the endpoints. Again, we can't use calculus on those endpoints because they're endpoints. But we can use the algebra. We can plug it into the function and see what their y values are to tell whether they're a minimum or a maximum, a relative or a absolute. Okay. And again, so here, working with that same example, and they're just going off the graph. This is a relative minimum, relative minimum. This one is the absolute y because it is the lowest. It's the lowest of the low. Relative maximum because in their area they're the top of the hill. Okay, one's a little bit more higher than the other, but they're both relative maximums. It's the endpoint here that is the very highest of the highs. Okay, so the endpoint here, and then what happens out here, well, that's not in the domain, so we're done. This is our limited domain, is going from A to B. Okay, so we can just identify them by sight. That's one way. We're going to see the use of calculus next to actually do this. So for stationary points, we can use the calculus. We can find where the derivative is equal to 0 and then solve for x. That will give us the locations. To get whether that location is a minimum maximum, then we'd have to plug in. There's another test that we can do a couple tests, but singular points, though, you can't take the derivative because it's where the derivative is not defined, but you can identify them. So once you do take the derivative, where is the derivative undefined? That's going to be a singular point. Okay. Because the reason it's not defined is we got a sharp point either going down or sharp point going up. So you'll be able to identify those. So find the derivative, set it equal to 0, and find where it's not defined. That will give you all the critical points, right? So I'll put that, these are going to be these two together are your critical points. Now again, the only time you even need to worry about singular points is if you've got a fractional exponent or absolute values, but those are the ones we're going to have. So you'll see it. It's a fractional exponents. There'll be a fifth power, a 1/5, 1/3. So there'll be odd powers, odd fractional powers. That's where we'll have singular points. There's 2 in the homework. You'll identify. I think there's only 2. Pretty sure there's only 2. And then remember, we come back. We can't do it with calculus, but we check the endpoints with algebra. We plug the endpoint values into the function to see if they're the highs or the lows. Okay, and compare. Okay, so those will give us all our extremums. Find the corresponding point x and y on the graph using f. So we find each of these. So we find all the critical points or critical values. Those are the locations where those happen. Those are the x values. We have the x values of the endpoints. We plug those into the original function, not the derivative function, the original function, to get the actual function values, to get the y values. Okay. And so a couple examples. Notice here is a cubic. You can take the derivative. The derivative of x cubed minus 12x is right here. Set it equal to 0. And if you solve for x, you'll get that x is plus or minus 2. So we've got critical points at plus or minus 2. Take that plus or minus 2, plug it back into the original function. So negative 2 plugged into the original function gives us this, negative 2, 16. Positive 2 plugged into the original function gives us 2, negative 16. So this is the larger value than, positive 16 is larger than negative 16. So I think we could easily agree that this has got to be a maximum and this has got to be a minimum. Now, are they absolutes? Probably not, but we we would look at the graph and see that we've got something like this. And again, where this would be the point -2, 16, and this would be +2, 16. Okay, -16, right? +2, -16. So some of these, as you get doing this, you'll see you'll be able to kind of look at the graph anyway. You could go ahead and graph that one. Now here's where we're going to get a singular point again. Notice it's got a radical, a fractional exponent. So because when we take its derivative, we get this negative exponent. It goes down into the basement, and so x minus 1. So it's undefined when the derivative is undefined at 1. 1 minus 1 is 0. That's an undefined area. So that's a singular point. It's going to give us either a minimum or a maximum. So you plug it back into the original function. Okay, you can't plug it into the derivative function. It's undefined. But you can plug it into the original function. 1 minus 1 is 0. 0 to the 1/3 power is 0. 0 times 3 is 0. Okay, so when you plug in 1, you get a function value of 0. So this is a, again, we'd have to look. It's either a minimum or a maximum. But what we'll do is we'll look at a few ways to find that out. So now we're going to look at something, a particular example. We'll go through a few of these, and then we're going to be kind of done and get you working on the homework. Now they'll give us an interval, so remember we've got 2 endpoints. This is x equals, so we've got endpoints, x equals 0, x equals 4. Those are the endpoints. We want to find the y values, so we could plug those in, and those will give us y values. But we also want to look interior to this, so between 0 and 4. So on our graph between 0 and 4, we want to see what's happening here. And so let's go ahead and walk through the example they give us. Actually, yeah. Oh, I forgot, this one just kind of goes. So first we take its derivative. So that's, the 2 comes down, we get 2x, and then derivative of x is 1. So the 1 times -2 is 2. So here's our derivative. We set that, and to locate the critical points, notice there will not be any stationary points because we don't have there's no place where this derivative is undefined. This derivative has a domain of all real numbers. But the critical points are where it's equal to 0. Well, the critical stationary points are where it's equal to 0. Set it equal to 0, solve for x, so we get one value at x equals 1. So, we're going to get a value here. Knowing that it's a positive, from your experience, you could probably draw it. But what we'll do is 0 to 4 and x equals 1 is an interior of the domain. So what we need to do is locate the y values, it's our locations, right? Here's 1. So we want to see what's happening at 0. We need to get that y value. We need to get this y value at 1, and we need to get the y value at 4. And we'll sort of be able to draw the graph knowing that at 1 it's going to be either a minimum or a maximum. Okay. So yeah, we know there's no singular points because the derivative is defined everywhere. So we go ahead and look at the endpoints. Again, this is where we're going to x equals 0, 1, and 4. So those are the 2 endpoints with the 1 critical point. Plug it into the original function. Notice this is our original function. Get the y values. We can see -1 is lower than either of the on the 2 sides, and if you remember how a quadratic function works, it's U-shaped. We can pretty much at this point say, yeah, this is going to be an absolute minimum. And between the endpoints, so this is going to be a relative maximum because it's bigger than that one, but this would be our absolute max. We're kind of, just from looking at this, This is, we could also call it a relative minimum, but it is also we're going to see it's going to be the absolute minimum. Because there's no other places in the middle that give us the derivative equal to 0 or the derivative undefined. So it's kind of cool to be able to do these once we know these properties. We know that we've narrowed it down. That's the minimum value. So we can start putting in those points. So here's 0. Here's at 1 it was -1, and then 4. And, you know, realizing it's quadratic, we could say it probably looks like, well, maybe not as squiggly as that, but we could kind of, it's going to be something like that, and we can pretty much see that that's going to be an absolute minimum. And it's got a horizontal tangent line, right? So they did a little bit better job, maybe a much better job of drawing it. But this is what I mean, is go ahead and graph them first, and the concepts all fit there. But do take that derivative, and you know, you'll see, okay, yeah, that's where the derivative is equal to 0. And it'll help with when we get maybe more complicated stuff. So again, here they just labeled everything. We got an absolute minimum here. At x equals 1, the value is -1. Absolute maximum at x equals 4, the value is 8. Okay. So first derivative test. Now, let me say the reason we would use the first derivative test. Oftentimes, in business situations, we do not have a function for what's going on, but we have a lot of data. We have sales data. We have this data. We have we have attendance data. But you've got numbers, which are your function values, and you can look over time what's happening to these values, stock prices, whatever that may be. So you've got a bunch of values, and what you want to do is either make it into a function, or you can look what's happening. Oftentimes you know the rate of change at various times. Sometimes we get that. And so you know the derivative on one side of a value or the other, and this is where we can apply the first derivative test. Let me give you just a brief story. When I was in financial planning, we had a client who, and this was 25 years ago. Anyway, he had a company, and this is in Oregon, so plywood, wood products. He would buy veneer. That's what you use for your plywood and make plywood. That's what his factory did. However, he got very wise at watching the market for veneer. He would buy the veneer, but in watching the market, sometimes he could see he could make more money by buying and selling veneer rather than buying the veneer, turning it to plywood, and then selling it as plywood. He would actually make more money because, again, there's less costs in moving it off. So he became very successful at doing this, of watching the veneer market in a very special case. He had several children who were in the business. None of them picked up on it, at least not when I was there, because it was something he couldn't really explain what he did, but this is what he was watching derivatives, and he could tell when the market was going to go up and down, and so he would know when to buy, and that in a short time he'd be able to sell for a profit. How he did it, I would like to go back and interview him, because that is a great use of calculus. He didn't have a college education. He probably never took brief calculus, but he was applying the concepts that we're going to do. So now you, who are taking brief calculus and are a business major, and you'll have all this theory with you, can you do the same in your field? Can you get to the point where you can look at the data, the time data of what you're dealing with? Can you get to the point where you're going to be able to see these derivatives and be able to predict, I can buy here and sell there and make a profit, or whatever that may be? That's what this next step could help you with. Okay, so the first derivative test is we're looking, obvious as the name implies, we're looking at the derivative. And since there's a first derivative test, you're going to see there's also a second derivative test that we'll look at later. It's just a derivative of a derivative, and those become valuable and they use those kind of things in financial markets now. There are something that are called, do they call them derivatives? Yeah, they call them derivatives, a financial product. So we'll look at those, but a first derivative test is simply what we do is we find a critical point, like we did with the x, what was that, x squared minus 2x. We found a critical point at 1, and what we do is we look a little bit to the left, right? This is subtracting half a point, and a little bit to the right. And again, we could have gone to 1.5 if we wanted to balance it, but what they wanted to do is get values that were easy to calculate. So you plug in 2, you get 2. So, and notice this time with the first derivative test, as the name implies, we are actually using the derivative. So these are not function values. What we're really concentrating on here is the sign of the derivative. So the value of the derivative is not as important, maybe it's not important at all, is really the sign. The sign is negative, so it's going down. To the right, the sign is positive. We don't write it, but it is positive, so it's going up. And then at the critical point, the sign is neither positive or negative. The derivative is 0, so it's neither increasing or decreasing. It's constant. And you can see we are going down, constant, up. And now the constant is just at a point, so it's not really flat there. We can see that this, from the derivatives, we're coming down and then going back up. And we've got our tangent line here. We can see from this, by looking at the derivative equal to 0 and just a little bit to the left, a little bit to the right, we can find this. Again, when I was doing this, this is really the only way we could do it because we couldn't always get the graph, not easily, because of our technology. Our technology today, we can actually just graph it, look at it, and we'd be able to see that this is a minimum. But you're going to get situations where, again, you're just looking at data. And with practice, with knowledge of your particular field, you might be able to do like my client was able to do. Actually, it wasn't my client. I was more of an analyst at that day, so my boss's client. And we did, I think it was, we sort of did the same thing with, I did the same. I saw what he was doing. I applied it to the tax situation and why it was wise to buy into a particular product at a particular time. And we made a very nice commission on that. Again, applying this. I got the idea from him at the time, but knowing a person's psychology is very helpful. So this is, sometimes you can see this by just looking at the numbers. That's what this is about. So first derivative test, and again, this just walks you through it. They find the function, the value, not the function value, but the derivative value at a point to the left. And again, there's nothing sacred about 0.5. It's just any point to the left. We could have gone to 0.25. What we would find, though, is the way derivatives work, because if you've got a 0 derivative, you know it's either a minimum or maximum. Everything to the left and everything to the right, at least in that neighborhood, will be going in the same direction. Okay. There's some mathematical theorems and stuff that have been proven that show that that is the case. That's nature. When you go down to the bottom, you're always going down. Okay. And then they do the same thing here. It's greater than 0. Again, it's positive. And so its slope is increasing. And so this is just walking. So f is increasing on 1 to 4. So from 0 to 1, it's decreasing. So here's 0 to 1. And then from 1 to 4, it's increasing. And we saw that with the graph. Okay, so the U shape. But this is specifically with the calculus. Okay. And again, I don't know why they showed that again, but maybe they're summarizing it. I don't always like to read all of this, but we know at x equals 1, we must have a minimum because we're going down and then up. Just emphasizing. Had it gone the other way, had it gone up and then down, well, that would show us that we've got a maximum, right? So 2 options. If it's all constant, then I guess we've got a horizontal. I guess that could happen too, but unlikely. We would know that it would be 0 everywhere already, because that's a horizontal line. So yeah, y equals. So far so good. Hopefully it's going well. Let's again, more verbiage, just showing that when we look at the first derivative, we look to the left at some point, and again we say x equals c, some value. Again, in our example, c was 1. If it's negative to the, so positive to the left, negative to the right, that's a maximum. Positive to the left, negative to the right, there we got this maximum thing going on. If it's negative, the derivative is negative to the left and positive to the right, we've got this sort of thing, so we've got a minimum. So that's the first derivative test. And then, you know, if it's the same side on both sides, then it's neither a maximum or a minimum. That could happen in certain cases, I guess. But we're going to really focus on this, minimums and maximums. We'll take a look at that later. Okay, but there's instances where that could happen. Quick example of a stationary point. We really can do the same thing. If we know we've got a stationary point, we look a little bit to the left, a little bit to the right, and we look at its derivative. And here we've got a going up, coming down. So again, we could say it goes like that. It's got to be a maximum. Even though it's undefined, the derivative's undefined at 1, we can look at the derivative to either side. And that's what we've got for today. Let me just pull up. We'll discard these. Let's look at the homework, and I'll just kind of highlight to get you drawn into a little bit quicker. So we kind of looked at 1, and you see what they're. Come on. Okay, there we go. We're back in business. So we looked at 1, and you need to identify things as minimums, maximums, absolutes, and such, and what points they occur. And again, you can see the critical points here. You just pick them off the graph and the endpoints. Okay, so there's 1, there's 2. Just take the values off the graph. That's what we're going to do here. Take it off the graph. 3 questions, just getting those values. And now we've got one where we've got a function with no graph. My suggestion is go ahead and graph it. You will see these values looking between 0 and 3. Perfect way to find it. Okay. You can also use the first derivative test. You don't have to, but you can see all those values. Do the graph. This one, do the graph, and look between -2 and 2. Again, remember the endpoints may be places where you're going to get either a minimum or maximum generally. So you find all of those. It's an x cubed. You're going to get an the derivative will be an x squared, right? So you probably get 2 places interior. But graph it, look at the table of values, and again, we can talk about these in class as well. Here's one, the 2/3, that's going to have a stationary point. Remember, we just know it because there's going to be a place where the derivative is undefined. And you also have your 2 endpoints. So one of these will be a stationary point, and probably the other 2 will be the endpoints. 2/5, another stationary. So I told you there was 2. We're going to see that this has a stationary point. And there's not 2 endpoints. There's 0 to positive infinity. So we got to see what's going to be happening at infinity. Good one to graph. This one, again, graph it, look in this interval. You can also use the derivative functions. And then we get down to this last one. Again, they even say use graphing technology, find its derivative. Again, this one, 2/3, we're going to get a stationary point here. I actually did a quick graph of this, and you'll see the stationary point. It's kind of fun. And that's it. 9 questions. So work over these, and then we'll be looking at these in class together as well as some examples working through it. So this is kind of, watch the video, the lecture, start working on the homework, come to class with questions about what you're working on so we can understand the details. If if you're making mistakes, if you can share your work, a number of you students have been doing that, sending me through the email. If you share your work, I can help find where an error might have occurred. And a lot of times, you see me working them. It's a slight conceptual error. Not that you don't understand what you're doing. It's going from one. It's a copy error. You're thinking of so many different things at once, and then you write something else down. But then you can't see it, because at least that's my problem. I can't see my own errors a lot of time because I was thinking the right thing when I wrote it. I just happened to write the wrong thing. And so when I look at it again, I think back to how I was writing it down. I said, no, I know this is right. And I can't even spot it until someone else says, well, that should have been positive, not negative. And I look at, oh, you're absolutely right. How did I not see that? But sometimes we are too close to our own work, and we don't see the work. We see what we were thinking at the time, and we were thinking correctly. We just wrote it incorrectly. A lot of reasons for these, but that's where we can get the best bang for our buck. If you're having trouble with the calculator, maybe just snap a picture of what you got entered. A lot of times you're missing a parentheses or something as simple as that, but that causes a lot of problems. And sometimes we can spot those, and it builds our confidence, because you go, oh, conceptually I'm doing really well. I'm understanding this stuff. I'm just making some small computational type errors, but that's normal because there's a lot going on at this time. So anyway, let's keep moving forward, and in this chapter 12 we're going to keep applying and trying to make those connections to what you're doing as a business major, how you can apply this to your field. Keep thinking about it. You'll see some examples, but think about how you might be able to do this, the kind of data that comes in your particular field, if your supply chain, or there's so many interests. Since teaching this class, you guys have helped me understand a lot of different business fields I never knew about. I knew business management, wow, but there's so much else out there, especially with finance, and it just keeps expanding. So you're going to do so many interesting things. My goal is to help you to find those techniques that will help you stand out in your field, by being able to, again, try to see a little bit into the future. And sometimes you don't have to see that far into the future, but if you can get that little peek of what's going to happen tomorrow, sometimes that's enough. Sometimes just knowing what's going to happen in the next hour, right? So but just that little bit of a jump gives you that much more of an edge, and allows you to bring your skills and your way of seeing things into this world. And hopefully along with that, you're developing a great humanistic compassion for the people around you, because you've made it through this math class, right? And so you're doing things that is going to be good for everybody in the world. Those two things together, the skills to do powerful things and the heart to do compassionate things, put those together, we will have such a beautiful world, like we did 5 to 10,000 years ago. That's what I can see. I see back into the past, because I'm also a history major. This world 5 to 10,000 years ago was a less materialistic world, a more spiritually connected world, where compassion for the fellow person was paramount. Everybody had enough to eat. Now there's time. Anyway, but let's see if you can make our next 100 years much better than the last 100 years.